Section 4.1, Scatter Diagrams and Correlation. We will look at these 5 objectives in this section. Objective 1, we want to draw and interpret scatter diagrams. Remember that the response variable is the variable whose value can be explained by the value of our explanatory or predictor variable. A scatter diagram is a graph that shows the relationship between two quantitative variables measured on the same individual. Each individual in the data set is represented by a point in the scatter diagram. The explanatory variable is plotted on the horizontal axis, and the response variable is plotted on the vertical axis. So let's look at this example. The data shown to the right are based on a study for drilling rock. The researchers wanted to determine whether the time it takes to dry drill a distance of 5 feet in rock increases with the depth at which the drilling begins. So the depth at which the drilling begins is our explanatory variable, or our x variable. And the time in minutes to drill 5 feet is the response variable, or the y variable. Now we'll look at drawing a scatter diagram of the data. So we have our data in the upper corner here, and we've plotted each point. And this is what our scatter diagram will look like. Notice that the depth, our x variable, is along the horizontal axis, and our time, which is our y variable, is along the vertical axis. So this point here would represent our 50 and 5.99, which was the second data value in our set. So let's look at creating scatter diagrams on our TI-83 calculator. The first thing to do is to enter the explanatory variable in list 1 and the response variable in list 2. So on our calculator, we press the Stat button first and then hit Enter to edit. And we see our lists. List 1 is where we want to list our x variables from our data. So we begin typing our first data point and then hit Enter, and notice that it begins to populate our list. And we continue on with all the data for our x variable. And now we're ready to arrow over to list 2. And we'll begin entering the data for our y variable. Notice that we have the same number of data values in list 1 and list 2. Once we've entered our data values in our 2 lists, the second step is to press the second button, or the orange button, and then to press y equals, which is right above it. This will bring up our stat plot menu. We want to select the number 1 for the first plot. The third step, we want to turn that plot 1 on by highlighting the on button, and you'll see it's flashing, and then pressing Enter. The fourth step, we want to highlight the scatter diagram icon and press Enter. Under Type, it's the first picture, and we press Enter on that. We want to be sure that the X list is list 1 and the Y list is list 2, and they are. Now we press Zoom, which is the middle button across the top, and we want to select Zoom 9 for Zoom Stat. And you'll notice we have a scatter diagram very similar to the one we just saw. If you press the Trace button, it will allow you to go between the points and see what their x and y coordinates are. And you see that this one, just as it was in the other picture, is our point 50 and 5.99. Here are pictures of the various types of relations in a scatter diagram. Notice that in all the pictures, the explanatory variable is across the horizontal axis and the response variable is across the vertical axis. In the first two pictures, A and B, we see a linear relationship. In picture A, this relationship slants upward. In picture B, it slants downward. Notice in pictures C and D, we have nonlinear relationships. And then in picture E, there is no relation that exists here between our explanatory and response variables. When this happens, it typically looks like chickenpox. Two variables that are linearly related are positively associated when above average values of one variable are associated with above average values of the other variable, and below average values of one variable are associated with below average values of the other variable. That is to say, two variables are positively associated if, whenever the value of one variable increases, the value of the other variable also increases. Two variables that are linearly related are negatively associated when above average values of one variable are associated with below average values of the other variable. In other words, two variables are negatively associated if, whenever the value of one variable increases, the value of the other variable decreases. Objective 2, we want to describe the properties of the linear correlation coefficient. The linear correlation coefficient, or Pearson product moment correlation coefficient, is a measure of the strength and direction of the linear relation between two quantitative variables. The Greek letter rho represents the population correlation coefficient, and R represents the sample correlation coefficient. We will only look at the formula for the sample correlation coefficient. And here we see that formula for R. The letter X with a bar, or X bar, is the sample mean of the explanatory variable. S with a subscript of X is the sample standard deviation of our explanatory variable. Y bar is the sample mean of the response variable. S sub Y is the sample standard deviation of the response variable. And N is the number of individuals in the sample. The linear correlation coefficient has the following properties. First, our letter R for the linear correlation coefficient will always be a value between -1 and 1 inclusive, meaning that it could also be -1 or 1 and anything in between. If R equals +1, then a perfect positive linear relation exists between the two variables. If R equals -1, then a perfect negative linear relation exists between the two variables. The closer R is to +1, the stronger is the evidence of positive association between the two variables. The closer R is to -1, the stronger is the evidence of negative association between the two variables. If R is close to 0, then little or no evidence exists of a linear relation between the two variables. So R close to 0 does not imply no relation, just no linear relation. The linear correlation coefficient is a unitless measure of association, so the unit of measure for X and Y plays no role in the interpretation of R. The correlation coefficient is not resistant. Therefore, an observation that does not follow the overall pattern of the data could affect the value of the linear correlation coefficient. And here we have a visual of these varying values for R. In A, R is equal to exactly +1, so it's a perfect positive linear relation. In D, R is equal to -1, so we have a perfect negative linear relation. And notice that both of those, the dots are in an exact straight line. In B and E, R is close to +1 or close to -1. So you see that the points gather in a line, either in the positive direction or the negative direction. For C and F, we notice that both of those values are just under the halfway mark. In C, R is approximately 0.4. In F, it's approximately -0.4. The sign simply determines the slant of the line. The closer it was to 0, either positive or negative, the less the points are to being in that straight line. So notice in G and H, both of those R values are close to 0, and we have no linear relationship existing. However, notice in H, that tends to look like some sort of relationship. It's just nonlinear. Objective 3. Compute and interpret the linear correlation coefficient. In this example, we're going to look back at our drilling data from the first example, and we want to determine the linear correlation coefficient, or R. First, we look at doing it by hand. We'll use the calculator to help us out with some of the values. Recall that we've already entered our value in the list. So if we press Stat and hit Enter on Edit, we see that our values are already still there in List 1 and List 2. So if we press Stat again, arrow over to Calc, and arrow down to number 2 for 2 variable stats, and hit Enter, and then hit Enter, we'll see that we get some of the values that we need for our formula. X bar is 126.25, and the standard deviation for X is 52.22874. If we arrow down, we'll get the values for our Y variable. Y bar is 6.985833, and the standard deviation for Y is 0.780774. Now we can use our list 3. If we hit Enter and go over to list 3 and up into the header, we can have it calculate this column for us. So we put a parenthesis, and we want to take all of the values in list 1, which was our X list. We want to subtract the X bar, which was 126.25. We close our parentheses, and then we wish to divide by the standard deviation of X. We hit Enter, and we see the same values populating list 3 that we have in this column here. If I arrow over to list 4 and up to the header, I want to take our Y values, so those were in list 2, and subtract our Y bar, and we divide that by the standard deviation of Y. We hit Enter and see that that list is now populated with the values that are in our column. This last column, we'll arrow over to list 5, and in the header we simply want to take list 3 and multiply it by list 4. Notice I'm hitting second and then that number, so second 4 will put list 4 in there. And I hit Enter, and now I have the same values that are in this last column. And I want to add the values in the last column. So let me quit, hit second and mode, and clear. If you hit second and stat, and arrow over to math, number 5 will sum, and I want to sum the values in list 5. So I hit second and 5. And we see we get the same number. So to compute R, we take the sum of our values in list 5 and divide it by n minus 1. N, remember, was 12 in this case. So 12 minus 1 is 11. We're taking our sum divided by 11, and we get 0.773. Let's look at doing this on our TI-83 calculator with a shorter method. The first step is to turn the diagnostics on. We want to select the catalog by hitting the second button and 0. This takes us into the catalog. We can either arrow down till we find diagnostic on, or hit this X to the -1 key, which will take us to the D's, and arrow down to diagnostic on. Once there, we hit enter, and hit enter again till it says done. Recall that our information is still in list 1 and list 2, so we'll hit stat and enter. And look back to see that we have list 1 and list 2. We'll go ahead and clear list 3 and list 4. I'll arrow up to the header, hit the clear button, and hit enter to clear it. We'll do the same for our last 2 lists. Hit clear and enter, clear and enter. So those lists are empty, so that we see all we needed was list 1 and list 2. Once those are in place, we hit the Stat button, arrow over till we highlight the Calc menu, and we'll select number 4 for LinReg AX plus B. Once that's on the screen, we press Enter. And we can see that our correlation coefficient, R, is listed right at the bottom. Objective 4, we want to determine whether a linear relation exists between 2 variables. When testing for a linear relation, the first step is to determine the absolute value of the correlation coefficient. Step 2 is to find the critical value in Table 2 from Appendix A for the given sample size. When working these problems, this table will be given to you. Step 3, if the absolute value of the correlation coefficient is greater than the critical value, we say a linear relation exists between the 2 variables. Otherwise, no linear relation exists. In this example, we want to determine whether a linear relation exists between the time to drill 5 feet and the depth at which the drilling begins. Comment on the type of relation that appears to exist between the time to drill the 5 feet and the depth at which drilling begins. So here is the table from the appendix that you'll be given with the critical values for our correlation coefficient. The correlation between drilling depth and time to drill was 0.773, as we calculated previously. Notice in this table that the critical value for n equal 12 observations is 0.576. Since 0.773 is greater than 0.576, there is a positive linear relation between time to drill 5 feet and the depth at which drilling begins. In Objective 5, we will explain the difference between correlation and causation. According to data obtained from the Statistical Abstract of the United States, the correlation between the percentage of the female population with a bachelor's degree and the percentage of births to unmarried mothers since 1990 is 0.940. Does this mean that a higher percentage of females with bachelor's degrees causes a higher percentage of births to unmarried mothers? Certainly not. The correlation exists only because both percentages have been increasing since 1990. It is this relation that causes the high correlation. In general, time series data, or data collected over time, may have high correlations because each variable is moving in a specific direction over time, both either going up or down over time, one increasing while the other is decreasing over time. When data are observational, we cannot claim a causal relation exists between two variables. We can only claim causality when the data are collected through a designed experiment. Another way that two variables can be related, even though there is not a causal relation, is through a lurking variable. A lurking variable is related to both the explanatory and response variable. For example, ice cream sales and crime rates have a very high correlation. Does this mean that local governments should shut down all ice cream shops? No. The lurking variable is temperature. As air temperature rises, both ice cream sales and crime rates rise. In this example, we want to look at lurking variables in a bone mineral density study. Because colas tend to replace healthier beverages, and colas contain caffeine and phosphoric acid, researchers and associates wanted to know whether cola consumption is associated with lower bone mineral density in women. The table lists the typical number of cans of cola consumed in a week and the femoral neck bone mineral density for a sample of 15 women. The data were collected through a prospective cohort study. The figure below shows the scatter diagram of the data. The correlation between number of colas per week and bone mineral density is negative 0.806. The critical value for correlation with n equal 15 from our table in Appendix A is 0.514. Because the absolute value of negative 0.806 is greater than 0.514, remember that the absolute value will make it positive, we conclude a negative linear relation exists between number of colas consumed and bone mineral density. Can the authors conclude that an increase in the number of colas consumed causes a decrease in bone mineral density? Let's identify some lurking variables in the study. In prospective cohort studies, data are collected on a group of subjects through questionnaires and surveys over time. Therefore, the data are observational, so the researchers cannot claim that increased cola consumption causes a decrease in bone mineral density. Some lurking variables in the study that could confound the results are body mass index, height, smoking, alcohol consumption, calcium intake, and physical activity. The authors were careful to say that increased cola consumption is associated with lower bone mineral density because of potential lurking variables. They never stated that increased cola consumption causes lower bone mineral density.